Hello students, the topic that we are going to cover today is moving charges and magnetism NCERT exercise. This is disclaimer. So the topics or the questions that we are going to cover today is in chapter moving charges and magnetism. There are total 13 questions of exercise. And in this lecture, we are going to cover 10 questions, 4.1, 4.2, 4.3, 4.5, 4.6, 4.7, 4.8, 4.9, 4.10 and 4.11. So the learning objectives, after this lecture, you will be able to calculate magnetic fields produced by current carrying conductors using relevant formulas, determine magnetic forces on current carrying conductors in magnetic fields including force per unit length, compute torque experienced by current loops placed in uniform magnetic field at different orientations, analyze characteristics of moving coil meters including their current and voltage sensitivities, calculate the radius of circular path followed by charged particle moving perpendicular to uniform magnetic field. So first question, exercise 4.1. A circular coil of wire consisting of 100 turns, each of radius 8 centimeter, carries a current 0.4 ampere. So what is the magnitude of magnetic field B at the center of the coil? Okay, so N is given, number of turns, radius is given. You have to convert all the given quantities in SI units. Current is given 0.4 ampere, and you have to calculate the magnitude of magnetic field at the center of the coil. So I will give you some time to think about it. So let's see the solution. So what are the given things? We have to list it first. So what is given? Number of turns on the circular coil N equal to 100. Radius of each turn are equal to 8 centimeter, which is in meter 0.08 meter. Current flowing in the coil I equal to 0.4 ampere. So what is the magnitude of magnetic field at the center of the coil is given by. Okay, so what is the expression for magnetic field at the center of the coil? So which is magnitude of B. We are going to find only magnitude, not direction. So magnitude of B, that bold B is magnetic field with direction. So we are taking mod. That means only magnitude equal to mu naught n I upon 2r. If there is only one turn, then mu naught I upon 2r. Okay, there are 100 turns, so we have to multiply it with n also. So mark it as first equation. So where mu naught is the permeability of free space, and its value is 4 pi into 10 raised power minus 7 Tesla meter ampere inverse. So B is equal to 4 pi into 10 raised power minus 7 into n is 100 into what is current 0.4 upon 2 into 10 raised power 2 into 0.08. So after simplifying, putting the value of pi equal to 3.14. So B is equal to 4 into 10, 3.14 into 10 raised power minus 7 into 100 into 0.4 upon 2 into 10, 0.08. So 4 into 3.14 is 12.56 into 10 raised power minus 7, and 100 into 0.4 is 40 upon 2 into 10 raised power 2 into 0.08. So after multiplying 12.56 into 40, it will result 502.4 into 10 raised power minus 7 upon 2 into 0.08. So B is equal to 3140 into 10 raised power minus 7. So the magnitude of magnetic field B at the center of the coil is 3.14 into 10 raised power minus 4 Tesla. So the magnitude of magnetic field at the center of the coil is 3.14 into 10 raised power minus 4 Tesla. So another question, exercise 4.2. A long straight wire carries a current of 35 ampere. What is the magnitude of field B at a point 20 centimeter from the wire? Okay, so there is a long straight wire. Okay, I is given 35 ampere, and the point where we have to find the magnetic field, magnitude of magnetic field from the wire, the distance of this point from the wire is 20 centimeter. Okay, we have to find the magnitude of magnetic field. So I will give you some time to solve it. So you have to remember all the formulae of this chapter to solve the numerical problem. So let's see the solution. So what is given? Current in the long straight wire I equal to 35 ampere. Distance of a point from the wire R equal to 20 centimeter, and it is 0.2 meter. Okay, so distance from the wire to the point where we have to find the magnetic field. So magnitude of magnetic field due to long straight current carrying conductor at a distance R is given by, what is the expression for it? B is equal to mu naught I upon 2 pi R by Ampere circuital law. Okay, so we have found this expression or relation using Ampere circuital law. So it is B equal to mu naught I upon 2 pi R. So mark it as first equation. Now we are not taking mod here because we have not written B as bold font. Okay, we have a normal font B. We have written B as normal font, which also means it is magnitude. Okay, so if it is written in bold font, that means it is magnetic field with direction. So then we have to put mod sign to find the magnitude. Okay, so these are the two notations for magnitude, where mu naught equal to permeability of free space, which is equal to 4.10 per minus 7 Tesla meter per ampere. So substituting given values in equation 1, we get B equal to 4 pi into 10 to the power minus 7 into 35 upon 2 pi into 0.2. So B equal to, so pi and pi get cancelled out, and 2 and 4 also get cancelled out, and it will result in 2. So 2 into 10 to the power minus 7 into 35 upon 0.2. So B equal to 17 to 10 to the power minus 7 upon 0.2. So B equal to 70 into 10 to the power minus 7, and 0.2 will become 2 upon 10. So 10 will go in the numerator. So 10 into 10 upon 2. So it will result in 315 to 10 to the power minus 7. So magnitude of magnetic field is given by 3.5 into 10 to the power minus 5 Tesla. Hence the magnitude of magnetic field at a point 20 centimeter from the wire is 3.5 into 10 to the power minus 5 Tesla. Okay, so all the students, you can type the answer if you have solved before me in the comment section also, and then verify. So next question, exercise 4.3. A long straight wire in the horizontal plane carries a current 50 ampere in north to south direction. Okay, so from north to south direction, long straight wire is carrying current 50 ampere. Give the magnitude as well as direction of B magnetic field at a point 2.5 meter east of the wire. Okay, wire is placed horizontal. Current is flowing from north to south. We have to find the magnitude and magnetic and direction of magnetic field at a point 2.5 meter in the east direction of the wire. Okay, so you have to mark the directions first: north, south, west, east, west. Okay, so you have to make the directions first. Okay, then you have to mark the direction of current and the point, in which direction point is there. Then you have to find the direction of this. So I will give you some time to solve it. So let's see the solution. So what is given? Current in the wire I equal to 50 ampere. Distance of point from the wire towards each direction R equal to 2.5 meter. Magnitude of magnetic field due to a long straight current carrying wire at a distance R is given by. So due to a long straight wire, magnitude of magnetic field at a point R from R distance from the wire is given by B equal to mu naught I upon 2 pi R. Okay. So where mu naught equal to permeability of free space, which is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. So substituting given values in equation 1, we get B equal to 4 pi into 10 to the power minus 7. This is the value of mu naught into I. What is I? 50 ampere upon 2 pi. What is R here? 2.5 meter. So B equal to 2 into 10 to the power minus 7 into 50 upon 2.5. Pi and pi will get cancelled out and 2 and 4 will get cancelled out and result in 2. So B equal to 2 into 10 to the power minus 7 into 20, which is equal to 40 into 10 to the power minus 7. So finally magnitude of magnetic field is given by 4 into 10 to the power minus 6 Tesla. Now we have to find the direction. So direction of magnetic field at a point can be found using right hand thumb rule. So you have to point your thumb in the direction of current, which is from north to south direction. Now curl your fingers. This point is in the east direction of the wire. So you have to point your thumb from north to south and in the east direction. So you have to see what is the direction of magnetic field at that point in the east. So using the right hand thumb rule, point your thumb in the direction of current north to the south and your finger will curl around the wire. At a point east of the wire, your fingers will point out of the plane of the paper. Thus magnitude of magnetic field is 4 into 10 to the power minus 6 Tesla and directed vertically upward at point 2.5 meter east of the wire. Okay, you have to point your thumb in the south direction because current is from north to south. Now you have to curl your fingers and in the east direction where point is located, your finger will point in the upward direction. Okay, curl your fingers, your finger will point in the upward direction in the east of the wire. Okay, so the magnitude of magnetic field is given by 4 into 10 to the power minus 6 Tesla and directed vertically upward at point 2.5 meter east of the wire. Got it? So next question, exercise 4.5. What is the magnitude of magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30 degree with the direction of uniform magnetic field of 0.15 Tesla? Okay, so we have to find the force per unit length. Okay, so on a wire carrying current 8 ampere making angle 30 degree with the direction of uniform magnetic field. Okay, so magnetic field, the magnitude of magnetic field is also given, angle is theta is also given, and current is also given. So what is the formula for force on a current carrying conductor? Then you have to divide it by length. Then it will result in force per unit length. So I will give you some time to solve it. So let's see the solution. given current in the wire I equal to 8 ampere, magnitude of uniform magnetic field B equal to 0.15 Tesla, angle between the current and magnetic field is also given, theta equal to 30 degree, and magnitude of magnetic force. So force on a current carrying conductor placed in uniform magnetic field is equal to I L cross B, and which is equal to I L B sine theta and n cap with direction. If we have to find only the magnitude of magnetic force, then it will be F equal to I L B sine theta only. Okay. Now we have to find the force per unit length. So you have to divide it by L also. So F equal to magnitude of this magnetic force is equal to IBL sine theta. From where this expression came? From F equal to I L cross B. Okay. So we are not considering the direction, only magnitude. So it will be IBL sine theta. So where L is the length of the wire. Therefore, magnitude of magnetic force per unit length of the wire is given by. So what is the magnetic force per unit length? This is the magnetic force on the whole conductor. So per unit length is F equal to capital F upon L, which is IBL sine theta upon L, which will result in IB sine theta. So F will be equal to what is I? 8 ampere. What is a magnetic field? 0.15 Tesla into sine theta is 30 degree. Okay, so sine 30 degree is 1 by 2 or 0.5. So F equal to 8 into 0.15 into 1 by 2, because sine 30 degree is 1 by 2. So after solving, force per unit length on the wire is equal to 0.6 Newton per meter. So it is force per unit length. So unit will be Newton per meter, not Newton. Hence the magnetic force per unit length on the wire is 0.6 Newton per meter. Okay. Next question, exercise 4.6. A 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? Okay, so we have to find the magnetic force. Okay, so this wire is placed perpendicular to the axis of a solenoid. So we know that inside the solenoid, the magnetic field is parallel to the axis of solenoid. We have placed the wire perpendicular to the axis of solenoid. So the angle between L vector and B is 90 degree here. Okay. So length of the wire is given, current is given, magnetic field magnitude is given. So you have to find the magnetic force on the wire. So I will give you some time to think about it. So what is the solution and what is given in the question? We will list it first. Length of the wire L equal to 3 centimeter, which is 0.03 meter. Current flowing in the wire I equal to 10 ampere. Magnetic field inside the solenoid B equal to 0.27 Tesla. The magnetic field inside the solenoid is directed along its axis and the wire is placed perpendicular to its axis. Okay, so magnetic field inside the solenoid is along the axis. We have placed the wire perpendicular to the axis. So the angle between the current carrying wire and magnetic field will be 90 degree. Means the angle between L vector and B vector will be 90 degree. It means when we do I L cross B, I L B sin theta, so this theta will be 90 degree. Magnetic force exerted on the wire due to magnetic field B is given as F equal to BIL sin theta. This is the magnitude of force. So put the values. B is 0.27 Tesla, current is I is 10 ampere, length is 0.03 meter into sine 90 degree. So F is equal to 0.27 into 10 into 0.03 into sine 90 degree is 1. So F is equal to, after solving, 0.081. So force is equal to 8.1 into 10 raised to power minus 2 Newton. So this is the magnetic force on the wire placed inside the solenoid. Hence, the magnetic force on the wire is 8.1 into 10 raised to power minus 2 Tesla. So next question, exercise 4.7. Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. Okay, so both the current carrying conductors are very long. Okay, we have to find the force only on 10 centimeter section of A, not on whole conductor A, only 10 centimeter section. Okay, current through both the wires or conductors is given 8 ampere and 5 ampere respectively, and both the currents are parallel in the same direction. Okay, and both the conductors are separated by 4 centimeter. So let's see the solution. So I will give you some time to think about it. So let's see the solution. So what are given things? First one is current flowing in wire A, which is IA, given 8 ampere. Current flowing in wire B, IB, which is equal to 5 ampere. Distance between the two wires D is equal to 4 centimeter, which is equal to 0.04 meter. Length of the section of the wire A, for which we have to find the force, equal to 10 centimeter, equal to 0.1 meter. Okay, so magnitude of force exerted on wire A due to current carrying wire B is FAB is equal to mu naught IA IB L upon 2 pi D. Okay, so force per unit length is given by, we have derived for force per unit length, which was mu naught IA IB upon 2 pi D. This is force per unit length. But now we are considering the 10 centimeter section of wire. Okay, so we have to multiply the force per unit length with L. Okay, so when we are going to find the force per unit length, then we don't have to multiply it with L. Now we are considering the length other than unit length. What is unit length? 1 meter. But now we are considering 10 centimeter. So we have to multiply the force per unit length with L to calculate the force on the 10 centimeter section of wire. So FAB, force on A conductor due to B conductor, due to magnetic field produced by B conductor, is equal to mu naught IA IB L upon 2 pi D. Mark it as one equation where mu naught is permeability of free space having value 4 pi into 10 to the power minus 7 Tesla meter per ampere. So substituting all the values in equation 1, So FAB will be equal to 4 pi into 10 to the power minus 7 into IA, which is 8 ampere, into IB, which is 5 ampere, into the length, which is 0.1 meter, upon 2 pi into D. D is 0.04 meter. So FAB will be equal to 2 into 10 to the power minus 7 into 4 upon 0.04. So FAB equal to 8 into 10 to the power minus 7 upon 0.04. So FAB will be equal to 8 into 10 to the power minus 7, and 1 by 0.04 will be 25. So 25 into 8 will be 200. So FAB will be equal to 200 into 10 to the power minus 7. So final answer is, what is the force on 10 centimeter section of wire? A is FAB equal to 2 into 10 to the power minus 5 Newton. Thus the magnitude of force on wire A due to wire B, FAB, is 2 into 10 to the power minus 5 Newton. Two parallel current carrying wires attract each other, while anti-parallel current carrying wires repel. Okay, so we have derived the conclusion in our theory section that if two conductors are carrying current in the same direction, then they will attract, and if they are carrying current in the opposite direction, then they will repel. Okay, it is opposite of the electrostatic behavior. In electrostatic, like charges repel, but here parallel currents attract. Okay, so it is reverse of electrostatic behavior. So two parallel current carrying wires attract each other, while the anti-parallel current carrying wires repel. We have given two parallel currents. In question, we have written that two parallel straight wires carrying current in the same direction. Okay, so carrying wires. So we have given two parallel current carrying wires. Wire A is attracted towards wire B. Therefore, the direction of FAB force is towards the wire B, because wire B is attracting the wire A. So direction of FAB will be towards the wire B. So next question, exercise 4.8. A closely wound solenoid 80 centimeter long. Okay, so length is given 80 centimeter. Has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of B inside the solenoid near its center. Okay, so we have to find the, because at the ends the magnetic field is not uniform. Okay, so we are going to find the magnitude of magnetic field inside the solenoid near its center. Okay, so the formula B equal to mu naught small n I, that formula we have derived for long solenoid, for which diameter is much less than the length of the solenoid. So this is applicable for only long solenoids, for which length is relatively very large as compared to diameter or radius. Okay, now the solenoid is having 5 layers of winding. Each layer has 400 turns. Okay, so we have to calculate the total number of turns first. Diameter is given, length is given, and magnetic field is also given. Current is also given. Okay, sorry, current is also given. We have to find the magnitude of magnetic field inside the solenoid. So I will give you some time to think about it. So let's see the solution. So what is given in the question? Length of the solenoid is given 80 centimeter, which is 0.8 meter. There are 5 layers of windings of 400 turns each of the solenoid. Each winding has 400 turns, and there are, each layer has 400 turns, and there are total 5 layers. Okay, so total number of turns on the solenoid is given by number of layers multiplied by number of turns in each layer. Okay, so total number of turns can be given by there are 400 turns in each layer and there are 5 layers. So you have to multiply the number of layers into number of turns in each layer. Thus n is equal to 5 into 400, which is equal to 2000. So total number of turns are 2000, 5 layers and 400 turns in each layer. So diameter of the solenoid is also given 1.8 centimeter, which is 0.018 meter. So if we are going to find the area, so pi d square by 4. So this 0.018 will get squared and value will reduce further. So area of cross section is very small as compared to length. Okay, or we can say diameter is also very small as compared to the length. Length is 0.8 meter and diameter is 0.018 meter. Okay, so current carried by the solenoid is also given I equal to 8 ampere. So since length is much greater than the diameter, so magnitude of magnetic field, now we can use the formula of long solenoid. Or also we are finding the magnitude of magnetic field near its center. So near its center, magnetic field is uniform. So if there is short solenoid, not long, we can apply that formula for long solenoid at or near the center only. We cannot apply away from, we cannot apply that formula for long solenoid for short solenoid away from the center. Okay, only we can apply that formula for long solenoids or for short solenoids where we have to find the magnetic field near its center or at center, because near the ends magnetic field is non-uniform. So here length is much greater than d, and also we are going to find the magnitude of magnetic field inside the solenoid near its center. So we can apply the formula B equal to mu naught Ni. What is small n here? Number of turns per unit length. So mark it as one equation. So where mu naught is equal to permeability of free space equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. So here small n is equal to total number of turns per unit length, which is equal to capital N upon N. So equation 1 becomes, indicates B equal to mu naught capital N upon L into I. So now substituting all the values in equation 1, so it will result in B equal to 4 pi into 10 to the power minus 7 into 2000 into 8 upon 0.8. So after putting all the values, what is the length? 0.8 meter. What is total number of turns? 2000. And what is current? 8 ampere. So B equal to 64,000 pi into 10 to the power minus 7 upon 0.8. So B is equal to 8 pi into 10 to the power minus 3. So it will result in 8 into 3.142, which is value of pi, into 10 to the power minus 3. So final answer is B is equal to 2.51 into 10 to the power minus 2 Tesla. The magnitude of magnetic field inside the solenoid near its center is 2.51 into 10 to the power minus 2 Tesla. Okay. So let's move on to next question. Exercise 4.9. A square coil of side 10 centimeter consists of 20 turns and carries a current 12 ampere. The coil is suspended vertically and the normal to plane of the coil makes an angle of 30 degree with the direction of uniform horizontal magnetic field of magnitude 0.8 Tesla. Okay, so coil is given, side of the coil is given, it is square coil, you have to find the area of the square coil. Okay, number of turns is given, current is given, and it is suspended vertically from the normal of the plane, and the normal of the plane is making 30 degree angle with the direction of uniform magnetic field. Okay, magnitude of magnetic field is given, you have to find the magnitude of torque experienced by the coil. So what is torque? M cross B, which is MB sin theta magnitude of torque is mb sin theta. What is m? Magnetic moment, which is equal to NIA. N is the number of turns, I is the current, and A is the area. So now torque will become NIAB sin theta. Okay. So I will give you some time to solve it. So let's see the solution. So what is given in the question? Side of the square is given L equal to 10 centimeter, which is 0.1 meter. Current flowing in the coil is given I equal to 12 ampere. Number of turns on the coil is given N equal to 20. Magnitude of magnetic field is given B equal to 0.8 Tesla. Angle made by normal to the plane of. Now what is theta here? We are not taking theta as the angle between plane of the coil and magnetic field. We are taking theta as angle between normal to the plane of coil, that is area vector also. Okay, normal to the plane of coil with the magnetic field. Okay, so theta here is 30 degree. So magnitude of magnetic torque experienced by the coil in the magnetic field is given by the relation tau is equal to NBIA. So what is NIA? Is M. Torque is MB sin theta. So what is M? NIA. So after putting, torque will become NBIA sin theta. So A is the area of the coil, which is given by, because it is square coil, so A is equal to L cross L, which is 0.1 into 0.1 equal to 0.01 meter square. So after substituting all the values in the torque expression, you will get tau is equal to what is N20, what is B 0.2, 0.8 into what is current 12 ampere into A 0.01 into sine 30 degree. Sine 30 degree is 0.5 or 1 by 2. So tau is equal to 20 into 0.8 into 12 into 0.01 into 0.5, because sine 30 degree is 0.5. So after solving, tau will become 16 into 0.06. So final result, the magnitude of torque experienced by the coil is 0.96 Newton meter. Hence the magnitude of torque experienced by the coil is 0.96 Newton meter. Okay, exercise 4.10. So let's see the listen the question carefully. Two moving coil meters, that is galvanometers. Okay, so two moving coil meters M1 and M2 having the following particulars. For M1 R1, resistance of first meter R1 is equal to 10 ohm. Number of turns of the first moving coil meter is 30. Area of coil of first moving meter is A1, which is equal to 3.6 into 10 to the power minus 3 meter square. And magnetic field of permanent magnets placed in first moving coil meter is 0.25 Tesla. Okay, so for M1, for first moving coil meter, these specifications are given. R1 is equal to 10 ohm resistance. Number of turns N1 is equal to 30. Area of the coil A1 is equal to 3.6 into 10 to the power minus 3 meter square, and magnetic field of the poles is given by 0.25 Tesla. For second moving coil meter M2, R2 is given 14 ampere, 14 ohm. Number of turns N2 is 42. Area of the coil A2 is equal to 1.8 into 10 to the power minus 3 meter square, and magnetic field B2 is equal to 0.5 Tesla. Magnetic field of the poles, cylindrical poles. The spring constants are identical for the 2 meters. Okay, for both the meters, spring constant are identical. Okay, that is also torsional constant. We have studied in the moving coil galvanometers. So K value is same for both the meters. Determine the ratio of current sensitivities of M2 and M1 and voltage sensitivity of M2 and M1. So you have to determine the ratio of current sensitivity of M1 and M2 and M1 and voltage sensitivity of M2 and M1. So I will give you some time to think about it. Let's see the solution. So what is given for moving coil meter M1? R1 is given 10 ohm. Number of turns N1 is 30. Area of cross section A1 is 3.6 into 10 by minus 3 meter square. Magnetic field strength B1 is equal to 0.25 Tesla. And spring constant K1 is equal to K. Okay. For moving coil meter M2, resistance R2 is given 14 ohm. Number of turns N2 is given 42. Area of cross section A2 is given by 1.8 into 10 per minus 3 meter square. Magnetic field strength B2 is 0.5 Tesla. Spring constant K2 as well as K1 equal to K. Spring constants are same for both the meters. So now A part, we have to calculate the current sensitivities of M2 and M1, then taking the ratio. Then after that we will take the ratio. So current sensitivity of M1 is, what is current sensitivity? Phi upon I. Okay, we have done in the theory section. Phi upon I. What is phi? NAB upon K into I. So phi upon I will be NBA upon K. Okay, so current sensitivity for first meter will be IS1, which is equal to N1 B1 A1 upon K1. And current sensitivity for second meter M2 is given as IS2 will be equal to N2 B2 A2 upon K2. Okay, now we will take the ratio. Ratio of current sensitivity of M2 and M1, IS2 upon IS1 equal to, what is IS2? N2 B2 A2 upon K2. What is IS1? N1 B1 A1 upon K1. Okay, so after simplifying, it will result in N2 B2 A2 K1 upon K2 N1 B1 A1. Now K1 and K2 is same. Okay, which is equal to K, because spring constant for both the meters is identical. So this K1 and K2 will get cancelled out from the equation. So IS2 by IS1, after putting all the values, what is N2 42, what is B2 0.5, what is A2 1.8 into 10 to the minus 3 into what is K1 equal to K upon what is K2 K. What is N1 30, what is B1 0.25, what is A1 3.6 into 10 to the minus 3. After solving it, it will result in 1.4 and K will get cancel out. So ratio of current sensitivity of M2 and M1 is IS2 by IS1, which is equal to 1.4. So ratio of current sensitivity of M1 to M2 to M1 is 1.4. Okay. Now we have to find the voltage sensitivity. B part, voltage sensitivity of for M2 is given as VS2 equal to N2 B2 A2 upon K2 R2. Okay. So what is voltage sensitivity? Phi upon V. So what is VIR? So phi upon IR. So phi upon I is current sensitivity, and also R is there in the denominator. So N2 B2 A2 upon K2 is current sensitivity, and upon R in the denominator it will result in voltage sensitivity. We have done the expression in our previous lecture. So voltage sensitivity for M2 is given as Vs2 equal to N2 B2 A2 upon K2 R2. So and voltage sensitivity for M1 is given as Vs1 equal to N1 B1 A1 upon K1 R1. Okay. Now we will take the ratio. So ratio of voltage sensitivity of M2 and M1, Vs2 upon Vs1. So what is Vs2? N2 B2 A2 upon K2 R2 into what is Vs1 N1 B1 A1 upon K1 R1. Since it is in denominator, so expression will get reversed. Equal to, after simplifying, it will result in N2 B2 A2 K1 R1 upon K2 R2 N1 B1 A1. Now again K1 and K2 are equal, so they will get cancelled out, and after putting all the values, so N2 is 42, B2 is 0.5, A2 is 1.8 into 10 to the power minus 3, and K1 is K, R1 is 10 upon K2 is K, R2 is 14, N1 is 30, B1 is 0.25, and A1 is 3.6 into 10 to the power minus 3. After solving it, it will result in 1. Okay. So Vs2 upon Vs1 will result in equal to 1. So the ratio of voltage sensitivity of M2 to M1 is 1. Okay. So our next question, exercise 4.11. In a chamber, a uniform magnetic field of 6.5 Gauss. 1 Gauss is CGS unit of magnetic field. 1 Gauss is equal to 10 to the power minus 4 Tesla is maintained. Okay, in a chamber, uniform magnetic field of 6.5 Gauss is maintained. 1 Gauss is 10 to the power minus 4 Tesla. We will convert it into SI unit also. An electron is shot into the field with the speed of 4.8 into 10 to the power 6 meter per second, normal to the field. It means the angle between the velocity and magnetic field is 90 degree, because we have shot an electron in the normal to the field. Explain why the path of the electron is circle. You have to explain why path of the electron is circle. Determine the radius of circular orbit also. So E is given 1.5 into 10 to the power minus 19. It is not given 1.6 into 10 to the power minus 19. So you have to take the value which is given in the question also. So E is given 1.5 into 10 to the power minus 19 coulomb, and mass of the electron is given 9.1 into 10 to the power minus 31 kg. So I will give you some time to think about it. So let's see the solution. So what is given? Magnetic field strength B equal to 6.5 Gauss, which is equal to 6.5 into 10 to the power minus 4 Tesla. Speed of the electron is given V equal to 4.8 into 10 to the power 6 meter per second. And this electron is shot normal to the field. And charge on the electron is given E equal to 1.5 into 10 to the power minus 19 coulomb. Mass of the electron is given Me equal to 9.1 into 10 to the power minus 31 kg. Angle between the velocity and the electron, velocity of electron and magnetic field is also given, theta equal to 90 degree. Magnetic force exerted on the electron in the magnetic field is given as F equal to, so what was the magnetic force on the charged particle? Q V cross B, which is Q VB sin theta n cap with direction, but magnitude is given as Q VB sin theta. Okay, so here Q is So charge particle is electron. So Q will be E. So E will be sine theta. Or theta is 90 degree here. So force will be EVB because sine 90 degree is 1. The direction of this force is perpendicular to both V and B. So you have to find the direction of force using right hand rule for vector products. Okay. So you can also use Fleming's left hand rule, but you may get confused that when to use the Fleming left hand rule and when to use right hand rule for vector product. So that's why I have not mentioned in the theory section Fleming's left hand rule. So in the entire chapter, you should attach to one rule, either Fleming left hand rule, either right hand rule for vector products. It will be easy for you and there will be less confusion. Okay, so you have to stick to one rule, either Fleming left hand rule or right hand rule for vector products. Okay, so right hand rule for vector product is more convenient to use. That's why I suggest to you use right hand rule for vector products. Okay, so the direction of force is perpendicular to both V and B. So you have to align your fingers in the direction of velocity of the electron and curl the fingers towards the magnetic field. Thumb will give the direction of the force. So you can see that when we do cross product, then the result of this cross product will be perpendicular to both the vectors that are involved in the cross product. So V cross B. So this force will be perpendicular to both velocity and magnetic field. Okay. So direction of magnetic force can be found using right hand rule for vector product. This perpendicular magnetic force. Now magnetic force is perpendicular to velocity. So this perpendicular magnetic force changes the direction of velocity of electron continuously without changing its magnitude. Why is it not changing the magnitude of the velocity? Because to change the magnitude of the velocity, there must be a component of force parallel to the velocity. Okay, if there exists a component of force parallel to the velocity, then the magnitude of the velocity will get changed. But here, force is perpendicular to the velocity. So it will change only the direction of velocity, not changing its magnitude. So magnitude of the velocity changes only if there exists a parallel component of magnetic force along velocity. Hence, magnetic force provides necessary centripetal force to move electron in a circular path. Okay, so this, because force is perpendicular at each step to the velocity, so it will provide centripetal force to the electron to move in the circular path. That's why the path of the electron is circle. Okay, now we have to find the radius of that circular orbit. So R be the radius of circular path of electron given by, and we know that what is the formula for radius. We have derived it by comparing centripetal force with the magnetic force. That is QVB equal to mv square by r. So from there, r came out to be mv upon qb. So here m is me. Here mass of charge particle is mass of electron, because a charge particle given is electron and q is e. After putting this in this expression, so me is 9.1 into 10 to the minus 31 into what is v, 4 into 4.8 into 10 to the 6 upon what is charge on electron, 1.5 into 10 to the minus 19 into what is b, 6.5 into 10 to the minus 4. Okay, and r will be equal to 9.1 into 10 to 4.8 into 10 to the minus 31 into 10 to the 6 upon 6.5 into 1.5 into 10 to the minus 4 into 10 to the minus 19. So r will be equal to 43.68 into 10 to the minus 25 upon 9.75 into 10 to the minus 23 equal to 4.48 into 10 to the minus 2. So r will be equal to 4.48 into 1 by 100. So radius is 0.0448 meter. Okay, so it will came out to be in SI units, because we have used all the physical quantities in the SI units. Now R will be, this is in meter, 0.0448 meter. So in centimeters, r will be equal to 4.48 centimeters. So radius of the circular orbit. So hence radius of the circular orbit of the electron is 4.48 centimeters. So thank you. I hope you enjoyed the session and all your doubts regarding solving problems have been clear.